Sure. All right, I'm Leslie Sturmer with the University of Florida Shellfish Aquaculture Extension Program, and I have the pleasure of talking about the various water chemistry parameters that were measured in our participating facilities, looking at the role of pH, alkalinity, and calcium carbonate, which actually turned out to be pretty fascinating information. So unfortunately, to get started, we've got to go with some definitions, and I'll wake you up when I'm through with that. But let's start with pH. So I think everybody knows what that is, and that's the measure of concentration of hydrogen ions in the water. It's a logarithmic scale from 0 to 14, 7 being the neutral value. And actually, it's an inverse scale where the more hydrogen ions, the higher acidity, but the lower the pH. And rapid changes can cause stress to aquatic animals. That's why we're concerned about pH. All right, alkalinity. Now that's the measure of water to buffer pH and to neutralize acids. So alkaline compounds, particularly your bicarbonates and carbonates, remove hydrogen ions by combining with them, making new compounds, lowering the acidity of water, thus increasing pH. And this provides proper levels of pH, which reduces stress in aquatic animals. So you want high alkalinity values. The source of alkalinity can be found in calcium carbonate. Limestone, for example, is nothing but calcium carbonate. It's the most abundant mineral on Earth. The primary calcium carbonate minerals are calcite and aragonite, and they're created in water when calcium ions react with those carbonate ions. Hardness, calcium hardness. It's the amount of calcium along with other minerals like magnesium and iron, they're generally divalent cations that are dissolved in water. So calcium in itself is an alkaline earth metal, but in water, the ion itself binds routinely with negatively charged alkalinity anions, bicarbonate and carbonate ions. You're going to hear about this throughout the presentation. That forms calcium carbonate. So there's some daily variations with these parameters, primarily due to photosynthesis of phytoplankton. And we know that photosynthesis is the process by which phytoplankton and plants create energy by using sunlight and carbon dioxide, which increases the pH. Now at night, photosynthesis stops, respiration occurs, that creates carbon dioxide and decreases pH. And just the graph on the left just shows when high and low alkalinity water, that diurnal variation with the buffering of high alkalinity water, minimizing that variation of pH over a 24-hour period. They also can vary seasonally, both due to temperature and rainfall. So as temperature increases, so does the capability of pH and alkalinity. It decreases due to increased carbon dioxide. Rainwater, slightly acidic, and that will also contribute to lowering of alkalinity or calcium carbonate. The take-home message on this variability to a seed producer is dilution of salt water by significant rainfall, fresh water, whether runoff or riverine sources, anthropogenic inputs, and other sources may cause pH, alkalinity, and calcium carbonate to vary. So there's multiple ways to measure these parameters. You've got aquarium and field test kits, sensors, probes, meters. They're inexpensive, readily available, and very easy to use. But you do want to monitor these parameters at the same time during the day due to those normal pH changes we just talked about. You do want to consider the accuracy of these test kits and meters. So the equipment used in this project was, we did a handheld meter for pH. The HANA marine kit for alkalinity, for example, that has an accuracy of plus or minus 5%. And then the calcium hardness samples, those were sampled biweekly, sent to the Harbor Branch lab and used a hot spectrophotometer for those measurements. All right, why are these important for shellfish seed production? Well, calcium carbonate is used by mollusks to form and build their shells and necessary for proper shell development. Inadequate pH and alkalinity levels cause larval shell deformities and poor growth and survival. So hatchery rearing waters should mimic or resemble natural seawater chemistry. And here's some recommendations. pH, recommended level of 8.2, acceptable range of 7.8 to 8.4 for alkalinity, looking in this in terms of milligrams per liter. of calcium carbonate. We're looking at a recommended level of 150 to 180, acceptable range of 110 to 200, and hardness around 200. Typically, what's measured is pH and alkalinity. So again, let's look at some graphs, and this is from a clam hatchery that used well water. And we can see that, is this working? No. All right. All right, so this is the hatchery here is obviously the source water is well water, and you're seeing very steady salinities varying from 29 to 32 in the second sample year, and then very steady at about 30 in the first sample year. It's a well water. Looking at pH, then on the left, again, some variation within the two sample periods, and you got to remember that this is a log scale of 10. So actually it's a little bit more significantly varying, but all of the values are above 7.5. And alkalinity, very high alkalinity associated with this well water. And that's what we're seeing. There's a trend in that, by the way, with well waters using very shallow wells for hatchery production of seed. And all of these are above 130 milligrams per liter. Looking at the same parameters for a nursery, and obviously this nursery is using surface water. And for salinity, seeing that bumping up and down between 20 and 30 parts per thousand. But then in the spring of the second year, which is typical for where this nursery is located, we do see a drop in salinity, almost down to 10 over the months of March and April, very much due to riverine influence at that location. How does the alkalinity and pH react to that drop in salinity? And we look at that on the right-hand graph, and you'll see that alkalinity also drops down to the lowest of about 100 milligrams per liter. But nonetheless, the buffering capacity provided by that source does keep pH at a higher level, anywhere from 7.5 to a little bit of 8. All right, so these tables show the pH and alkalinity values for all of the participating seed production facilities. So on the right hand column of both tables here, we have the facility code, as well as we can identify whether it's a hatchery, H, or a nursery, N, as well as their source water, with SW being surface water, WW being well water, and TW is tank water. Then you want to look at the blue highlighted columns there for the averages in year 1 and year 2 for pH on the left table and alkalinity on the right-hand table. All right, let's look at these values real quick. So in terms of pH, we do see a couple of facilities that have pH values less than 7.5. They are both hatcheries using well water. Oops, I'm not doing that right. There we go. I'll have to use this. The hatchery using well water above, we're looking at pH averages of 7.0, but this is right from the reservoir. That was a question asked earlier. But in the tank water, the operator then aerates prior to stocking, and simply through that process of aeration and degassing the carbon dioxide, they're able to increase those pH values to acceptable levels. So how does that correspond with the alkalinity for those two? But I might mention that all the alkalinity values are high for those facilities in terms of averages, but how do they relate to those two hatcheries that we just looked at with the lower pHs? And you see, again, very high alkalinity values for those facilities. For all of the facilities, they're all greater than 110 milligrams per liter. All right, moving on. So when atmospheric carbon dioxide is absorbed or dissolved by the ocean, the chemistry of seawater changes. So water and carbon dioxide form hydrogen ions and carbonic acid, which then quickly goes into bicarbonate ions, lowering the pH. So as more carbon dioxide is dissolved, the levels increase excess hydrogen ions result in fewer available carbonate ions. And remember, we just talked about carbonate being important for shellfish. That phenomenon is referred to as ocean acidification. So in 2007, hatcheries in the Pacific Northwest began experiencing massive oyster larva mortalities. The problem turned out to be upwelling of carbon dioxide-rich oceanic waters, resulting in lower pH and aragonite saturation levels. And we know aragonite is one of the minerals of calcium carbonate. It's not the one most prevalent, but is the most soluble form available in water. And it is necessary for molluscan larvae to build to initiate their new shell. So the solution came to by simply just adding a buffering system to their water supply source to increase pH. Several years later in the in the Northeast, we also had hatcheries, particularly a very large one in Maine, begin experiencing larval production problems. So they looked to the Pacific Northwest, but they realized that the problem was different. It was decreased calcium carbonate saturation states due to increased atmospheric carbon dioxide and freshwater runoff from heavy rain events, acid rain, for example. But the solution was the same, and that was buffering their incoming water to increase that carbonate saturation state, and that resulted in better production. So what about the Southeast? Well, coastal waters tend to be well buffered with lower carbon dioxide and higher alkalinity levels. However, river water discharges due to, again, heavy rain events associated with tropical storms and hurricanes are the driving factors in carbonate chemistry. So impacts of climate change are likely to affect coastal water chemistry in the future. A little bit about shell development of larval bivalves. So the concentration of carbonate ions, we talked about that several times now, and dissolved calcium are the building blocks of shell. Post-fertilization, larvae immediately begin to capture ions from the seawater, combine with calcium to form aragonite. It's an energetically expensive process as larvae accrete more shell mass than organic mass during these first 1 to 2 to 4 days. Post-metamorphosis, juvenile shell is comprised of calcite, aragonite, or both minerals. And let's just look to the pictures on the left here. These are of Pacific oyster larvae from the same spawn. And on the far left column, you'll see normal shell development at 1, 2, and 4 days at a pH of 8.0. And then on the right, we see the pH was set at 7.5. You're beginning to see shell dissolution almost immediately and defect features. Talked a little bit about saturation states, but what does that mean? What is a saturation state? So it's the measured tendency of a mineral to form or dissolve in water. And it's calculated by the ratio of the mineral dissolved ions to a solubility or equilibrium product, which is based on a given temperature, salinity, and pressure. So we can determine saturation states for the 2 forms of calcium carbonate minerals that we're interested in, and it's expressed as the Greek letter omega. And right. So if the omega level is less than 1, then calcium carbonate can readily dissolve. It means it's a corrosive environment. If the omega level is greater than 1, then the calcium carbonate mineral forms, which is what you want. Calcifying bivalves, oysters and clams live in conditions where the omega values are greater than 1 and thrive in conditions where they're much greater than 1. For example, corals need omega levels of greater than 3 to form and grow. So we did the calculation of saturation levels for both calcite and aragonite at all of our production facilities. Again, hatcheries, nurseries, source water SW, for surface water, TW, tank water, well water was WW. We used a program that was developed by the Oak Ridge Lab and Department of Energy, where we could plug in the values like alkalinity, pH, salinity, temperature to estimate these saturation states. Again, they're going to be expressed as a ratio. I might just comment that for these values to be, these are estimates, For these values to be more precise, you can also plug in things like partial pressure, carbon dioxide, dissolved inorganic carbon, which these are not measurements that we took in the scope of this project. But let's go ahead. And again, you see facility code on the far left of each table. The highlighted blue columns are the average that we calculated. And all of these averages, again, for calcite saturation state are above 1 with a couple of exceptions. We see that at the, well, actually just one exception. We see that at that hatchery that we looked at earlier with the lower pH. But again, that was at the reservoir source. When we look at the tank water after aeration, we see we get values that are much greater than 1, which is acceptable. Again, calcite is the most abundant form. It's not surprising to see this, but let's look at the aragonite saturation levels. Again, in the blue highlighted columns here and here. And we do see where in hatcheries using surface water, values less than 1, as well as well waters, and as well as at nurseries using surface water. And all 3 of those nurseries are in one location, by the way. So what does that mean? Again, I would suggest that these are estimates. But I would look, if I was a hatchery operator and I was using surface water, I think that I would take advantage of the equipment that's being provided to you, which you'll receive at the end of the workshop. And I think I would measure pH and alkalinity. If not routinely, at least spot check it. And if you cannot increase those pH or alkalinity levels to more of an acceptable range, I think that I would start aerating. I think you all do anyway, but I would think if aeration would degas any of the excess carbon dioxide, maybe not so as important in surface water versus well water, then I might consider buffering my incoming water supply source to increase those levels of pH and alkalinity, which will drive that aragonite saturation state. For nurseries that are using surface water, what else are you going to use for nurseries? And you see lower aragonite levels. I don't think that's as concerning because at that point in time, juveniles are able to use calcite to continue to build their shell, which is readily available and into adulthood. So with that said, I guess, sorry. So point that out. So again, at this one hatchery that we continue to point out because we did also measure at the same time their tank water, we see again by degassing or aerating, you see you're increasing those levels of aragonite availability by that simple treatment. But let's look at a buffering system. And this is a picture of a setup at an oyster hatchery in Louisiana that was used to increase and maintain their pH and alkalinity levels, the components being. All right, so that's a reservoir tank that's used to store water to fill their larval rearing systems. Attached to that is a bracket that has a pH meter controller and pump with long cords that they can move to other reservoir tanks. And adjacent to that is a 55-gallon tank that contains a saturated solution of soda ash, which is not exactly baking soda, but a similar chemical compound. The brains of this operation is the meter, which measures pH of tank water, adds buffer, in this case soda ash, to achieve an optimal pH via an injection pump. And then the controller calculates the required injection rate and activates the system. This is not an expensive operation to put together. In fact, all the work is being done by this piece of equipment, and these are used routinely in hydroponic operations. This one in particular is something like close to $400. They can get much more expensive. So further information about water chemistry can be found in this fact sheet here. And of course, all of this is going to be posted on the webpage dedicated to this project. So with that, I will take any questions you may have. Want me to go over those definitions again? Yeah. Yeah.
Now, why exactly are all the hatchery sites listed as anonymous?
That was the agreement we made with those hatchery operators. These are commercial operations. That's the agreement we made for them to participate in the project.
Thank you.
Thank you. Considering the increased degree of variance, both seasonally, like due to natural weather, and then any discharge that could be anthropogenic or unpredictable, is there any potential argument going forward with scale for having recirculation hatcheries where you're creating your water and having control de novo? You know, because if you're able to sustain that level of control, if it's, because it seems to me, you know, if you're entirely relying on these wild water bodies and there's a big rainstorm that happens, you know, there's only so much buffering capacity you can have when you're relying on wild water. Is there, I'm sorry, in your opinion, will there be any transition you think towards a recirculation kind of approach with this where you can have complete control and that compensates for the extra infrastructure and cost because, you know, you're not having 90% mortality every other month?
Okay, so the question is, given these variation in water quality parameters, is there any consideration to having recirculation as opposed to for your hatchery, as opposed to reliance on surface or well water? And I would say that there are some hatcheries that are considering recirculating systems and have been employed. The one hatchery that we looked at in the picture of the Louisiana has gone to a recirculating component, especially when they're having heavy flood stages and so forth. Yeah, I don't know how to answer it any further than that, but none of these participating hatcheries that we work with here in Florida are based on recirculation. All right.
The buffers, hi Leslie. The buffer system that you show, that's mainly for static tanks or in a hatchery situation.
Yeah.
Yeah.
That was adjusting the reservoir water.
So like in a flow through system in raceways or upwellers, could you use something else besides soda ash, like a limestone bed or something to possibly raise the pH and those things?
pH is a problem. And I might mention,
Or to add the,
I mean, these are values that are approximate, that are guidelines, that's what the meters are for. The real key is, are you seeing flow growth, deformities in your facility? That's really the key. If you are, then you need to go back and look even further at these parameters, and is there a simple solution like aeration, or do you have to go to the next step of a buffering system? Again, in a nursery environment and a flow through for surface water, again, I just can say that calcite is just as important at that point in time for continued shell growth. But if you're thinking water chemistry is driving some problems you're having with your seed production at a juvenile stage, I don't know, it might be interesting. So throw a bunch of lime rock at the bottom of your tank. I don't know. Let it dissolve. I don't know.
yeah, we just see some years are much faster than others, and I'm not always convinced it's the phytoplankton.
Right.
But we've never been monitoring it, so it's interesting to see this. Yeah. Thank you.